So here's what we're going to do now. I mean, we have, first of all, thank you all for staying so long, and it's nice to see the audience still. Everyone is awake, so that's great. So what we'll do is that, so Zach, hi Zach, this is Professor Tetlock. He doesn't look like a professor, but he is, I promise. I'm just kidding, I didn't mean, just because I'm just kidding, Zach.
No, that's how you can tell. I just got tenure, so I'm wearing flip-flops.
He just got tenure, yeah. So what I would do, so Zach does programming languages. You know, he's behind a lot of the advising on the programming language aspects of the stack. So what I would do today, just in this last half an hour, is just do a discussion on, an open discussion on how we take this stack and this project to the next level. We put together a couple of discussion points here just to get started with. You know, one, for example, are there any big pieces missing in the stack that would enable broader use in research and deployment? I know we have, so who here is using this mostly for research? Most of you, right? Okay, and deployment? Few. The Amazon folks, thank you, yeah. So, any thoughts on how this would be more useful? Anything missing? Yeah? I see. A new backend, yeah, that's a very, very fair point. And I think it ties very much with the second point here. You know, what else can we automate with more machine learning or other automated reasoning, you know, or synthesis methods, right? For example, Megan has been looking at how can we use program synthesis to synthesize operator implementations from a specification. So you can imagine that as sort of like one step towards making it easier with automation, or just like plainly having a language that describe in a clean way what a harder backhand could be an interesting. Any thoughts on that?
I just started. Sorry, I was typing. I'm making a Google Doc for all of your great ideas, so I missed a couple of the details. But yeah, I mean, I think making it easier to target additional hardware. That's also partly the stuff with micro TVM, is to have very minimal requirements on what you need in order to deploy on a new hardware. And more synthesis for accelerators, I think, is also going to be really interesting. One thing that's challenging too, or we think might be interesting in the future, is that a lot of times, you know, you have to do a fair amount of work to get an operator tuned to a new accelerator to come up with schedules and all these things. So I think that as auto TVM matures, you're going to see that also becoming easier and easier. We've also been looking at automated tensorization, just like there are automatically parallelizing compilers for the HPC scientific computing community. We think that you can also probably do automatic tensorization and adopting some of those techniques. It's a little bit more challenging though, much higher dimensional data. How do you deal with sparsity, density? There's a lot of interesting research there. I think sort of that, you know, that's a lot of different fronts, but hopefully making progress on each of them is going to make it a lot easier to add new backends, new targets for TVM.
So another, I guess, building on that, so automating more the process would be interesting. So Zach mentioned a few, but some other things we're looking at as well. Things like how do we tune Vita parameters automatically? So there's an effort that Terry and Luis and a couple of others are focusing on called Auto Vita, on how do you express a objective function, like, you know, you want to hit a certain latency target or a certain power efficiency target, and then we, together with accuracy, explore the harder parameters automatically. So this hasn't been, we don't have anything out on that yet, but this is definitely on our radar. So a couple of other things here, like for example, yeah.
Oh, can I inject one?
Absolutely, yeah.
I was just thinking on this, maybe kind of almost a meta question. What do you folks think made LVM so successful?
Easy extensibility and much more accessible code than GCC had.
When you say accessible code, do you mean easier to read?
Yes.
So like the quality of the implementation, more readable, better documented code, and extensibility. So the extensibility of LVM is that a lot of things can make passes easily on the bit code, or there are a lot of front ends, so you could slurp in a lot of input from different languages, or there are a lot of back, or just all of these things. Like, what dimension of extensibility?
Well, for me personally, it's the passes at the IR level. The SSA-based,
So you could add new instructions.
and to transform instructions to fit a certain cost model. For example, if I have many parallel operators, as I can do in an FPGA, I have to use a different cost model than on the CPU, where I'm constrained with regard to parallelism and register space.
Yeah. Perfect.
But also second accessibility in terms of the code being accessible and easier too. That's close to my heart because in grad school, when I was hacking on GCC, right when LLVM was starting, I suffered a lot with, just understanding the code. And by the time I understood it, it was changing already, so it was. Plus in GCC, you have these source code lines that wrapped around 3 like across the screen because it's so long and hard to read,
As I just said, it's macro hell. You have to follow up multiple levels of macro interactions in GCC to figure out what's going on, what's actually going on.
Any other thoughts about maybe what made LLVM such a big hit and has had such a big impact?
As somebody who used it, just in the past year, like we just had to learn it in the past year, documentation and all of the infrastructure surrounding LLVM to make sure that it actually builds and works still.
Well, a lot of
This is, I think in the modern day, it's a little unfair to say this because LLVM is so widely adopted, but its documentation is what made it so easy to jump on.
And also debugging. Remember that LLVM probably still has it when you had the bug in a pass. It had this automatic way of reducing exactly where the bug is by isolating what was correct. So ease of debugging is important. And I guess we have here not only debugging in terms of correctness, but also debugging in terms of degraded accuracy, for example. How do you even specify that? Cool.
Any more thoughts on what has made LLVM such high impact? I think maybe one way to sum those ideas up, it sounds like the quality of the execution was a critical ingredient, like the design and the execution being very clean, well documented, sort of industry ready. So maybe a follow-up question to that though is that the right goal for us? I think in a lot of ways we want to be that infrastructure. We want to be the standard framework you reach for when you want to do something new and crazy because we have solved a lot of the hard problems in a fairly general way that you can slightly modify to do, scratch that itch you have. But is that what our goal should be? Are we, is that what people want? Could you use that? I think this is kind of what that first bullet is getting at, or should TVM be something different? What are you folks like? When you go home and you're on YouTube, you're listening to Luis and I again, what are you going to wish you'd had the courage to stand up and say now, right? It's a big ship. I mean, it's hard to change direction, but we want to know. Yeah.
One thing that there's an interesting blog post from Julia King on this, but is treating the machine learning stack separate from the software engineering stack, and having to choose which stack you're operating with at any given time, and as machine learning and software engineering continue to be used interchangeably amongst each other, then having these two separate stacks and interacting, it's not clear whether the domain specialization pays off or you get more than you get hurt by having interrupt.
Can I just try to repeat that back? So you're drawing a line between the machine learning stack and the software engineering stack. You mean that sort of there's like these two sort of distinct ecosystems. There's a set of compilers and tools and languages that we use kind of in building machine learning systems, and another set we use when we build sort of, I guess, discrete, integer, whatever, traditional systems. And that in that shuffle, there's some tension or?
Well, I guess probably even software engineering practices and tools. Like, for example, if you're building a system that has, say regular code plus machine learning modules that you call, and then the system misbehaves, just figure out how do you even start debugging, where is your bug and understanding performance and so on, right? Yeah.
One concrete kind of stab at unifying these is Chris's IR project, basically kind of trying to bring these two under one.
Right.
Yeah, and it's not even necessarily ML specific, right? It's like an IR ecosystem, yeah.
Cool. Can you talk a little bit about emerging models and at a higher level? We that we're ramping up an effort on supporting sparse data structures so we can better enable graph neural network models and also support for dynamic models that Relay is going to bring. Are there other things, and also support for training as well? So any opinion from the more machine learning focused folks in the audience? Any thoughts on supporting emerging models or?
How many people work on designs of new machine learning models?
3, okay.
So for you all, like what's, I mean, we have some notions, right? Our view of the problem moving, coming to this is, it's really annoying to do things like control flow recursion, custom data types. Those have been kind of bolted on generally, or they work nicely in general, like you have expressiveness, but you pay for it in performance. You know, is there a language feature that is more than just recursion, control flow, custom data types, loops? I don't know what, pattern matching. Is there some language feature for writing down a model that you think people should start thinking about now or might need? Or do you think that, you know, one way to think about Relay is sort of like standard ML is enough, right? If you have a Haskell-y looking functional IR, you can do about anything.
I'm doing work on some product networks, and part of those some product networks are histograms.
Some product, yeah. Mm-hmm. Great.
Thank you, yeah.
Cool. Now, so then going lower level, so support for emerging technologies and architectural trends. I know that, you know, we are, even though FCRC includes other communities, you know, there's a significant number of architects here, right? So one thought that has been in our minds for a while is that, you know, there's a bunch of architectural trends. It's only going to make hardware more complex as a target for programs, right? So you have things like non-volatile memory, processing memory, 3D integration. Let's just start with these you know, 3 architectural and device trends, right? So what are the implications for, you know, efficiently mapping machine learning models? One is if you have a much more complex memory hierarchy, it becomes even harder for you to extract performance out of it, right? So how do you keep everything busy as you have a more complex hardware fabric? And processing memory specifically is one that's interesting, right? So the trade-off there is that, you know, you have a lot more processing elements, but you have a lot more bandwidth to memory and potentially lower latency too. But now you have a placement problem, right? So when you have not only you have to choose where data goes to do the data layout, you also have to do computational layout, like where are you going to put each piece of your computation, right? So, and 3D integration is also interesting because it gives you very, very high bandwidth access to memory elements that could have significant implications on how you do compilation for machine learning, right? So, any thoughts from the more architecture-minded folks in the audience? Yeah.
I think one more interesting direction would be to look into reconfigurable hardware like FPGAs and all.
Right.
In my time, my mentor was really pushing on putting machine learning into edge devices with FPGA
Mm-hmm.
because of the performance per watt thing, and Microsoft is pushing in that.
Right, yeah, absolutely.
So I think that would be a nice addition.
Yeah. It's definitely interesting. Our approach to that right now has been with templates, right? But it'd be interesting to break free from templates and do an even more direct compilation from say, tensor expression traits to FPGAs. Let's say high-level synthesis applied to this, right? So, any other? How about Jan?
Well, it's also heterogeneity, right? So we
Right.
have the next generation of FPGAs,
Mm-hmm.
both traditional bit-oriented fabrics and these vector processors.
Right.
Scheduling and optimizing for those is going to be fascinating.
Absolutely, yeah. So to build on that, you know, as I guess it's pretty clear that a lot of the FPGA vendors are beefing up their fixed function, you know, elements, right? So, and that's even if they look like reconfigurable to some extent, you know, picking which ones to use is going to be interesting. The diversity is going to increase, right? So,
Memory systems where we're getting multiple channels of HBM.
yeah.
And deciding, you know, that the whole scheduling of what data, how do you organize the computation to keep more stuff in SRAM and lock room,
Right.
and how that trades off when you have more memory bandwidth to spare.
Yeah. That's right, heterogeneous memories too, right? Yeah, so one thought on that was, I know some people have been looking at when building training systems to read data straight from permanent, like straight from SSDs, right? So if you had a beefy giant array of disks where you streaming data from directly, can you actually schedule your computation and data movement in a way that you don't even buffer in any other memory, just go essentially straight from your SSDs or your permanent storage system straight into your tensor registers would be an interesting scheduling challenge too, right? So I guess pushes what Jan said to an extreme. Yeah.
Just an addition to that is true that one very good fascinating thing would be to explore training in a truly heterogeneous system with multiple different hardwares when all the hardwares are actually doing training.
Right.
Instead of just the GPU doing training.
Yeah.
So that would be a nice direction to kind of look into as well.
Right. Yeah.
It's just fascinating theory. It's very hard to probably
Mm-hmm.
deliver this thing.
Yeah, I guess just breaking out the training problem into elements that would be amenable to very heterogeneous compilation targets, right? So even as boxes, right? You can have a box with a bunch of CPUs. Yeah, got it. How about even more adventures? People have been talking about quantum machine learning for a while. There's people actually showing some interesting algorithms that the cool thing there is that people try to find quantum algorithms for machine learning for later to realize that, oh, it turns out that this has implication in the classical implementation that goes back to classical computers, right? So
It makes it better, yeah.
yeah. Okay, so in terms of community forming, any other ideas? So we definitely want this event here was very focused on hands-on use, like different than our conference in December. So we definitely want to have another conference probably in December as well to bring people together. But if you have other ideas for community formation, we'd love to hear them. We had the idea, for example, of having challenges. People would come up with, performance optimization challenges and solutions that we could give them, some kudos for doing that, or a leaderboard for good. Some people have a brain in a way that knows how to express search spaces in a way that is very efficient, like Eddie, for example. But any other ideas on how we get more community participation and growth? Yeah.
How about improving documentation?
Improving documentation, that's a great point. The best documenter, yeah.
Have you looked at the TVM docs?
Yeah, and I did not find the things I was looking for.
If you like anytime file an issue, please. So we are actively working on documentation. It's like every week we check in like who's making progress on which parts of the docs. We know that there's sort of a lot there and it's not necessarily organized top down. That's because we've been sort of writing docs for components as they're added. So one of our summer goals is to do a top-down sweep.
So to give you an idea how to go about this, think about how different kinds of users might start to enter the system. For example, for me, at this point in time, I'm a hardware guy. So the question I would like to ask, what would I have to change in TVM, what would I have to read in TVM to fit a certain hardware, which looks different from VDA?
Yeah.
Right. Yeah, no, it's a great point. So in fact, there was somebody, you brought up the idea of like, one of the things missing is making it easier to create new backends, right? Say that, having more backend creator focused documents, right? So documents people that are building new backends.
Maybe we have like 3 indices or something. Like you'd have like this is like I am a hardware designer of a new backend.
Exactly, that's what I meant.
Or I'm a compiler hacker. I want to write compiler passes, and like those are different views of the world.
Exactly.
And so maybe there should be structure that reflects that.
So, just on that point, I think it's really important that we address this. I think right now the documentation is insufficient. The other thing I'd like to add is that it really helps us address the problems when the hardware designs can be shared with the community, so we can generalize from one example that we can compile to multiple ones. Unfortunately, when we deal with corporations or startups, they cannot share their secret sauce. But I think this is an opportunity for academics or research group in industry that are open to open sourcing to really make an impact on building this ecosystem of open source hardware devices that are programmable by TVM, so we can generalize from Vita to other case studies, architectures that should look very different, and understand, how to do this across different types of devices. So I think that the people who are interested in going in this direction from a research standpoint, adding their own hardware devices to the TVM ecosystem should talk to me after this, and maybe we can think about concrete steps to build that. because the goal of Vita was not to build a design that, you know, would capture all of the acceleration efforts of the community, rather kind of an incentive to get other people to jump on board, present their accelerators that have also TVM support.
I think a lot of people also mentioned about accessibility in a sense that, you know, how easy it is to get my graduate students to work on
Mm-hmm.
that task and hack it so that it quickly support the things I want. One thing that's one thing we think a lot about in TVM. We try to learn a lot from PyTorch. By the spray that, you know, for example, there's another researcher, Michael Taylor. He's working on the accelerator, and we are trying to get a graduate student to work on supporting hardware backhands for their accelerator. And one advantage that TVM relays that have is that you can see in all the demos, it's all in our Python notebook. You can prototype all the optimization process in Python before you other than C++. And most of the graduate students I talk to like to write Python.
Mm-hmm.
Than C++.
Yeah.
So I think these are the perspectives we will
Yeah.
to also hammer on and while after those things become mature, we can get engineers to harden them in C++.
Yeah, so I guess, you know, I guess it can boil down to having virtual boot camps for TVM users. So there was a hand up there in the back. Yeah, hi.
One of the things I wanted to mention, I've just started looking at the source code. One of the things that we could probably learn from other projects like LLVM or GCC for that matter is comments in source code.
Comments in source code.
Yeah, and maybe making some of that part of the coding standards.
We should write a machine learning model to do that, yeah. I mean, this language generation, no, you're right, so I'm just, you're absolutely right, yeah.
And that tends to help people when they're looking.
Yeah.
Right now, I think we require public API comments for all the public API, but not necessarily on the implementation.
Not necessarily on the implementation.
That's something that we can
But for someone who's starting new on it, having the comments there with it actually help.
Mm-hmm.
Is-
Otherwise, it's a pretty steep
Right.
learning curve.
I mean, one thing would be identify the modules that somebody's most likely to copy, paste, and modify, and make sure those are heavily commented.
So a more procedural question here too, is that were the IPython notebooks and demos useful during the tutorial? Was that, yeah, Jan?
They were fantastic. We had to run through them very quickly.
Yeah.
Probably who has played Redmond before. How long are they going to be available? We come back at one, and we click on those links, and they still work.
We want them to be available, yeah. So,
I was going to say, because I did all the packaging. Right now, they're on a stable version of TVM. So if any people want them to be updated, we can talk about how to make that more possible. And they will be more, as long as collab works. Yeah. We can let them know about that.
well,
Yeah, so we have a tutorial which are different size of conversion. Some of them already exist in the
So I think the short answer is, as long as the infrastructure it's built on is up, they'll continue to work.
Right.
They will get out of date because TVM master moves pretty quick, but they should be relevant for.
I think I was going to say, like, I would like to make them like a stable piece of documentation, because I think it would be nice to evolve them into a book. Because I agree with your comment right now. I don't set open TVM, let's say, a year and a half, 2 years ago or something, and like the learning curve is very steep.
Yeah.
And it would be nice to have sort of a book to be able to. So,
Mhm.
yeah, I think there's two components to the notebooks that we showed today. One is the fact that you can deploy this in IPython form, so you can step through it. And we already have this space gallery of IPython notebook examples. It requires you to build TVM on your machine, which can be a little, tricky if you don't have the right dependencies installed, which is why Colab is really nice, because it can deploy it. So one thing that we've actually been talking internally is potentially having our space gallery of IPython notebooks have Colab integration, so we can run that in builds, and then make sure that, all those tutorials could be deployed from the browser. Actually, something that I did today, I had no idea it would work, I don't know if that's been done before in an architecture conference, but that might have been a first.
Cool.
Yeah, so I think that convenience of running things from a thin client and getting to learn about TVM without having to go through the installation process is
Yes.
eliminating
Right.
a huge adoption barrier, and
Right.
we should strive to do this.
I think some of those things are what we call like triage, just knowing that are visual versions and it has fun
Yeah, you can see that as a form of documentation. I mean, documentation came up before, right? So documenting the code, documenting the use, but also making IPython notebooks an integral part of documenting the project to be an interesting community effort as well, right? Yeah. Yeah, Jason.
One thing to think about is, with respect to LLVM comparisons, LLVM moves so fast with so many breaking changes that it actually causes a lot of challenges for industry users. And I know actually more than one story of large companies trying to pin versions and falling behind. But if you, especially at earlier stage of the project, you need that flexibility to change things in the environment, especially if you tackle all these difficult use cases.
Mm-hmm.
But in one model that LLVM uses for that is kind of the very core stable IR that evolves extremely slowly, and all of this running machinery level. So does TVM have stuff similar model, or
Mm-hmm.
might be something?
Relay in
That's a
a
good
lot of
point.
ways is, we hope, the future-proof IR, because we are exactly, this is the problem we're exactly worried about. And we just saw, every framework sort of like, let's bolt on a little bit of syntax for this feature, let's bolt on a little syntax for that feature, like, where does that end? And so we really hope, we don't have histogram support, so we'll see, we're gonna think about that. But we really tried in Relay to get a set of features that we think will be fairly robust in the future, and it'll at least evolve slowly. But it's a new thing, so it remains to be seen if that pans out that way. That is a goal, and we completely agree with that sentiment.
I think to add to that, I think one of the most important things also we have a core component to be modular. For example, you find that today we talk about micro TVM, Logan and Turkish, they don't have to worry about how to compile runtime because this is the job relay, and everything in runtime works naturally with relay and all the structures. So when we are trying to make those components modular so that you don't need to worry about one part of component, connect that to TVM, then you get all the models, all the simulations.
Mm-hmm. So I'll tell you a quick story here that about a year or so ago, Terry and I were teaching a class, and Tianchi was involved on hardware software co-design for machine learning. And there was this really interesting exercise that the students really liked, and we thought maybe we could reconsider doing this in a broader scale, which is essentially put together a Vita. At that time, Vita wasn't as developed, but there was a hardware component, there was a TVM stack on top, and then there was a model, and then we gave as a challenge to the students to optimize their implementation, right? And then put their solution on a accuracy versus energy or versus performance cost. And then we gave a little prize for everyone that was in Pareto Frontier. So I wonder whether we could, and then what's nice about that is that there's no single winner, right? Everyone, as long as you're in the Frontier, every time you submit one, you could see where you were in the Frontier. So maybe, we could try and make that another, a broader version of that, and putting like models that people really care about, and then make it very easy for people to, either improve the model or improve the implementation or create new optimization passes in TVM or make even changes to Vita, and then, show this in the, continuous leaderboard of accuracy versus computational cost. And that could be one of the challenge problems there. Any thoughts on that? Would that be useful? Would anyone here participate? One, all right, Songhan. Cool, we have one MIT professor. Okay, cool. That's good, all right. that should be enough, yeah. All right. Cool. Well, if you have any other ideas of things like that we could do, let us know, because that, helps get awareness and get more people involved too, so. Cool. Any other parting thoughts? No? Okay, well, thank you all again for coming, and thanks everyone like this, the team here put an incredible amount of effort to put the IPython notebooks and talks together, so they're the ones who did all of the work, so thank you. Thank you, guys. Thank you for, and we're going to stick around for, I think there was a little bit of ad hoc office hours for anyone who wants, right? Thank you.